Dear students, in the last lecture we have seen single beam and double beam colorimetry. So now in this lecture we are going to study spectrophotometer. So in that there are two spectrophotometers, single beam and double beam spectrophotometers. So the first, see this double beam spectrophotometer, sorry, single beam spectrophotometer. The source is there, collimating lens. It is similar to the colorimeter. A rotating monochromator is there, sample holder, focusing lens, photocell, amplifier and trade out. The figure is similar to the single beam, the near about similar to the single beam colorimeter. So in this case we are going to study the principle and how it works and what are the components of this spectrophotometer. So in this instrument, a monochromator, that is prism or diffraction grating produces a monochromatic beam. So in colorimeter we are used a source of radiation, and in that filter is there, that is color filter is there, and that color filter filtrate the narrow band of monochromatic light. But in this case a rotating monochromator is used, that is prism is used, and diffraction grating are used as a monochromator, and this prism or diffraction grating produces a monochromatic beam which is then made incident on the sample. The absorbance A or transmittance T of the sample solution is determined for different wavelength after adjusting the absorbance of the blank to 0 for each of the wavelengths. So in this case what we do, we are calculating the absorbance or transmittance of the sample solution for different wavelength by rotating this monochromator. So suppose if we are using a visible radiations at 400 nanometer, we are calculating the absorbance for the sample. At 500 nanometer, we are again calculating the absorbance for the same sample in the same cuvette. So after adjusting different wavelength of radiations, we are calculating the absorbance for the same sample. All measurements are done using a single optical path for the monochromatic beam of light. So here only a single optical path length of light is used for the measurement of absorbance or transmittance for the sample solution. Now see here, a single beam spectrophotometer has the following components. A source of radiation is there. Again monochromators are used. Third, a sample holder is there. Photocell is there, readout device. So the components for this spectrophotometer are similar to the components of the colorimeter. So the first component is a source of radiation. So tungsten lamp is used for obtaining a visible light. UV light is obtained from hydrogen or deuterium discharge lamp. So in your exam they will ask you, for the single beam spectrophotometer, the UV light is obtained from dash dash. So it is obtained from hydrogen lamp or it is obtained from tungsten lamp. So visible radiation is obtained from the tungsten lamp and UV radiation is obtained from the hydrogen or deuterium discharge lamp. The second component is monochromator. A monochromator, either a prism or a diffraction grating, disperse the light into its constituent wavelength. So what is the role of this monochromator? So monochromator disperse the light into its constituent wavelength, that is it disperse 400 nanometers different, 500, 600, so like that it disperse the light into its constituent wavelength. By rotating the monochromator, the different wavelengths are focused one by one on the sample. So in this monochromator we are just adjusting, or we are rotating the monochromator. So by rotating the monochromator, the different wavelength of lights are focused one by one on the sample. So by use of that we are calculating the absorbance at different wavelength of radiation. The third component is a sample holder or sample cell. The glass cuvettes are used in the visible region. Quartz cuvettes are used in the UV region since glass absorb UV light. So now see here, cuvettes are of glass or are of made from the quartz. So UV radiations absorb the glass absorbs the UV radiation. Therefore, uh, when the UV light of source is there, UV radiation is there as a source in case of single beam spectrophotometer, then for that we are using a quartz as a cuvette to that is hold the sample solution. But in case of visible radiation we are using a glass cuvette. So the fourth one is photocell. The transmitted beam emerging from the sample falls on the photocell. So whatever the light which is emerging from the sample holder or sample cell, it incident on the photocell. An electric current, just it is similar to the colorimeter. An electric current is produced due to the photo emission of electrons at the photocathode. If the current is small, it can be amplified using an electronic amplifier. So the working of photocell in case of colorimeter and in case of spectrophotometer is same here. Whatever the light which is transmitted from the sample cell, it is fall on the photocell and an electric current is generated, and that electric current is now amplified, and we are we have now the absorbance and transmittance value. So the last is readout device. It is a dial on which absorbance A or transmittance can be directly read, or a digital display will be there. So these are the components of this single beam spectrophotometer. So now we'll go for the working. Now see here, the sample holder is filled with the solvent. The absorbance value A of the solvent is adjusted to 0, or the transmittance is adjusted to 100%. That is, in a sample holder we are putting a solvent. So why it is called as a blank? Because now see here, in the same solvent we are preparing a sample solution, that is compound. The concentration of the compound which is going to be calculated is initially that is dissolved in the solvent. So when the sample is in the solvent, the same solvent is used as a blank for the determination of the concentration. The sample is then taken in the sample holder and its A value is determined for the same wavelength. The procedure is repeated for a different wavelength obtained by rotation of a monochromator. That is, when sample is put in the sample holder, we are calculating the absorbance for different wavelength of radiations. The procedure is repeated for a different wavelength, and then we come to an analysis for the result. If A or a transmittance values can be read either on dial or digital display, then after that we can calculate the lambda max value for the sample. So this is what the working of the single beam spectrophotometer. Now see this monochromator. So we just seen that is what are the monochromators used for the single beam. So we can use prism as a monochromator. We can use as a diffraction grating. So if you see this diffraction grating, it is made by cutting a large number of perfectly parallel straight lines into an aluminum surface. So on the aluminum surface there are large number of perfectly parallel straight lines are there, and for the UV and visible regions there are 15,000 to 30,000 lines are there per inch. Now you can imagine the small lines per inch are 15,000 to 30,000. So when the light is reflected at the grating surface, then there is a dispersion takes place, and due to the why dispersion takes place, it is because of the constructive interference of the reflected rays. Whatever the light is get reflected, it creates a constructive interference, and the net path difference between the two ray is an integral multiple of the wavelength and is given by this equation. So now see here, the light is reflected on the grating surface, dispersion takes place, and due to that, due to this constructive interference of the reflected rays, dispersion takes place, and the net path difference between the two rays is an integral multiple of wavelength and is given by the equation that is d is equal to n lambda, or n lambda is equal to d. So where n is nothing but order of interference and is a positive integer, lambda is wavelength of incident radiation, d is the distance between two successive grooves, that is lines, and it is constant for the prism, and I is the angle of incident of the beam, and theta is the angle of reflection of the emerging beam. The positive sign indicates that the incident and emerging beam are on the same side of the grating normal. If it is the negative sign is there, then it indicates that two beams either are on the either side of the grating normal. Now see this one, this figure 11, at the last figure, C is there. So if you see this incident radiation and reflected radiation, incident radiation having an angle of I and reflected radiation having angle of theta. The angle theta is different for different wavelength. Thus the light is dispersed into its constituent wavelength at the grating surface, and grating monochromators have certain distinct advantage over the prism. So what are the advantage over the prism? Now see here, a grating gives a much better dispersion of light than prism. Gratings are made of non-corrosive materials like aluminium, and gratings can be used over a longer wavelength range as compared to prism. So because of this advantage, most of the time for the spectrophotometer we use diffraction grating as a monochromator. So now next is a double beam spectrophotometer. So in the single beam spectrophotometer we have seen different components and how it works, and why the diffraction grating has more advantage over the prism as a monochromator in case of this spectrophotometer. Now see this single beam spectrophotometer diagram. So in this diagram the source of radiation is there. And it incident on collimating lens, and it comes now here to the rotating monochromator. So M1, M2, there are two mirrors are there. So one light goes to the sample cell and another beam of light, it is a double beam now, therefore one beam of light, that is light is get split into two beams. One beam goes through the sample cell and another goes through the blank cell. So when it passes through the sample cell, it comes to M4 and then it goes to detector. From the beam which is transmitting from this blank cell, it goes to M3 and then it comes to detector, and after that electronic amplifier is there and a recorder is there, pen, and because this pen is rotated on the drum with a chart paper and gives us a graphical representation. So by use of this method, by use of this instrument, we can easily determine the concentration of different solutions. Now see the explanation. In the double beam spectrophotometer, a monochromatic beam coming from a diffraction grating monochromator is split into two beams. So the beam initially split into two beams by means of mirror M1. Now the reference beam is reflected by mirror M2 into the blank cell containing the solvent. So in the blank cell the solvent is used, and in the sample cell we are using a sample solution. So the two beams are used here. One is going through the sample cell, another going through the blank cell. An optical attenuator mounted in the path of reference beam, now see this reference beam, that is blank cell, reduces its intensity to match that of the sample beam. That is, the amount of transmitted light coming from the blank is decreased so that its intensity is equal to the transmitted light coming from the sample. Now this attenuator is connected to a recorder pen which moves across the chart paper through a rotating drum. The two beams are then reflected by mirror M3 and M4 into a suitable detector here. And finally, the photocells are used as a detector in the UV and visible region. The detector produces an electric current which is proportional to the radiation received by it. So the electric current is produced by the radiation produced by this photocell. The electric current is magnified by use of an electronic amplifier, and the electric signal is sent to the recorder pane. So here the electric current is magnified then, and that magnified electric current is then sent to a recorder pen. A motor synchronizes the speed of the rotating monochromator with that of the rotating drum carrying the chart paper. As a result, the wavelength marked on the chart is identical with that received by the detector. So this is what the instrumentation part. So now comes to the last point is working of this double beam spectrophotometer. Now see here, the monochromator is rotated to allow different wavelength to fall on the blank and sample solution. This process is called scanning. So what we did in scanning, we are rotating the monochromator, and by rotating the monochromator, the different wavelength light fall one by one on the blank and sample. The recorder pane plots a graph of absorbance or transmittance versus wavelength. So this plane plot a graph of transmittance versus wavelength, or absorbance versus wavelength, frequency or wave number on the rotating drum. Now see this figure of absorption spectrum of benzene in the UV region. So in this case the absorbance is plotted against this wavelength. The wavelength at which maximum absorption occurs are noted on the respective spectra. Now see here, maximum absorption by the sample solution is plotted or noted on the respective spectra, and the groups responsible for this absorption or transmission are identified. So why there is a maximum absorption takes place at respective wavelength is identified because of the presence, and it is identified, and it is only it may be due to the presence of certain groups in the molecule. So the certain compounds gives lambda max value at certain wavelength. It is only the reason because of the presence of the functional group in the molecule. So different functional groups gives different lambda max value at different wavelength. So by use of that values we can determine the structure of sample. So it is a very simple method for the determination of the structure of different molecules by use of this maximum absorption value, that is lambda max. So now we are going to compare the comparison between the photometer and spectrophotometer. So what is the difference between this photometer and spectrophotometer? Now see, for the first one, photometers usually work in the visible region, while a spectrophotometer can work in UV, visible or IR region. So we can use this spectrophotometer in different regions of UV, visible and IR, but for the photometers we require only a visible region. So next difference is photometers use color filters which allow a band of wavelength of the complementary color of the sample to be incident on the sample. But in case of spectrophotometer, it employs a monochromator which produces perfectly monochromatic beams. Hence, spectrophotometric analysis is more accurate as the bandwidth of light beam is minimum here. Further, the Lambert-Spear's law is strictly obeyed for the monochromatic beams used in a spectrophotometer, but it is not happen in the photometer. Photometers are generally used for quantitative analysis of colored compounds, whereas spectrophotometers are used for structure determination of colorless as well as a colored compounds in addition to a quantitative analysis. So the photometers are usually used for the determination of colored compounds, and but in case of spectrophotometer we can use colorless as well as colored compounds. So spectrophotometers are much more costly than photometers. So this is what the difference between the photometer and spectrophotometer. So photometers usually works in visible radiations, but for spectrophotometers we can use visible UV and IR radiations. So in photometer we use color filters and which allow a band of wavelength of the complementary color of the sample. But in case of spectrophotometer, we employ monochromator, which produces perfectly monochromatic beam. And lastly, the Lambert's-Bates law is strictly obeyed by the monochromatic light beam, and it is obeyed by the spectrophotometer than photometer. And these photometers are generally used for quantitative analysis of colored compounds, but in case of spectrophotometers we can use it for the determination of colorless as well as colored compounds. So this is what the point here, the spectrophotometers, that is single beam and double beam. So only difference between the single and double is that in case of single, only single beam is used. For the double beam spectrometer, the light is gets split into two equal identical beams. One passes through the sample and another passes through the solvent cell. So this is what the single beam spectrophotometer and double beam spectrophotometer. Thank you.